Hello everyone, I am Minakshi working as an assistant professor IT department KIET group of institution Ghaziabad. In this lecture, I will be discussing about stacks and subroutines in 8085 microprocessor. So let's get started. What is a stack? A stack is a collection of data elements in a memory which follows the LIFO principle. So stack is an area of memory identified by the programmer for temporary storage. It is made for temporary storage of information. The stack is a LIFO structure, last in, first out. The element which is inserted last in this stack will be accessed first. Stack normally grows backwards into memory. In 8085 microprocessor, when stack is implemented in the memory, it grows backward. Backward means it grows from higher address to lower address. So here you can see that it is the bottom of a stack. The stack is growing backward from higher address to lower address. The programmer defines the bottom of the stack and the stack grows up into reducing address range. In 8085, stack is defined by setting SP, stack pointer. It stores the address of the top element of the stack. So here we have to put the address of top element into the stack register. To load the address in stack pointer, we will use LXI, load extended immediate instruction of 8085 microprocessor. This instruction will store FFFF into stack pointer. This sets the stack pointer to location FFFF. The size of a stack is limited only by the available memory. The information is inserted into the stack and the operation for inserting information into stack is called push operation. And whenever the information is retrieved from the stack is called a pop operation. So in 8085, we have two instructions. One is push, second is pop. For storing information on the stack and retrieving it back. To push the information into the stack and pop the information from the stack. Push and pop work with register pairs. So we have BC pair, DE pair, HL pair in 8085 microprocessor. So whenever we perform a push operation, suppose we want to put the data from register B and C into the stack. So we will write push B. This instruction will push the data from register B and C pair into the stack. Here, suppose SP is pointing to this location. So first we will decrement the stack pointer and we will put the data from register B to here. Then again we will decrement the stack pointer and put the data from the lower register here. So first the data from the higher register will be inserted and then the data from lower register will be inserted. In push instruction, which is 1 byte instruction, first we will decrement the stack pointer, then we will copy the content of register B. In this example, we have taken register B to the memory location pointed by stack pointer. Then again, we will decrement the stack pointer and copy the content of register C in this example to the memory location pointed by SP. And now we will set stack pointer to point top element of the stack. Push PSW. Push PSW, program status word. Program status word basically is the combination of accumulator and flag register. So in this instruction, we are going to put the content from accumulator and flag register into the stack. So here a register pair is accumulator and flag register. So push PSW instruction, which is also a 1 byte instruction. To implement this instruction, first we will decrement the stack pointer by 1 and then copy the content of register A. First we will insert the content from accumulator. Then we will decrement the stack pointer, copy the content of flag register. So the value in stack pointer is 100. It is pointing to the location 100. Then first we will decrement y1, that is 99. So we will put the content of accumulator at 99 location. Then we will decrement the stack pointer and we would put the data onto the next location. And finally, we will update the stack pointer to the updated location so that now it will point to the top element of the stack. For PSW, this is also a 1 byte instruction. Here, first we have inserted the content of register A and then content of register flag. Now, if we are going to pop from the stack, first the flag register data will be popped out. Then we will again increment the stack pointer and the data from stack will be popped out and will be inserted into accumulator. So first the content of memory location pointed by the stack pointer to the flag register and then increment the stack pointer. Then copy the content of memory location pointed by the stack pointer to the register A, that is accumulator, and then increment the stack pointer. Now, what is subroutine? A subroutine is a group of instructions, or we can say a subprogram. And it groups the set of instructions which will be used repeatedly in different locations of the program. And rather than repeat the same instructions several times, we can group these instructions into a subroutine that is called from the different location. We will perform the calling of subroutine. In assembly language, a subroutine can exist anywhere in the code. And it is customary to place subroutines separately from the main program. We cannot define the subroutine within the main program. In 8085, we have two instructions to implement subroutines: call instruction and return instruction. Call instruction is used to redirect program execution to the subroutine. Whenever a subroutine is required, we will call it and we will use the instruction call. When the subroutine has been executed by the processor, then control will return from the subroutine to the main program. So RET instruction is used to return the execution to the calling routine. In this example, you can see we have a call instruction here, call 2070, and this is 3-byte instruction. So this instruction will require 3 memory location: 2040, 2041 and 2042. And in this program, next instruction will start from 2043. Once the subroutine will be called, the control will be transferred to 2070 memory location. And here the subroutine is written. The subroutine will be executed, and when it ends, the control will be returned to the next instruction of the calling routine. So in this way, the subroutine is called and the control of execution is transferred to the location where the subroutine is written. Now the processor executes the subroutine. When it finishes, it returns to the next instruction of the calling routine. Call instruction. We can write a call and some address where we want to transfer the control or where the subroutine is returned. This is the syntax of call instruction. When call instruction is fetched, the microprocessor knows that the next two memory locations contain 16-bit subroutine address. Once the call opcode is fetched from the memory, the processor will know now the next 16-bit address will be the subroutine address. Now processor reads the subroutine address from the next two memory locations and stores the higher order 8-bit of address into W register and store lower order 8-bit of address into Z register. In 8085, W and Z register are the internal temporary registers. So if the address is 4000, so higher order 8-bit of the address will be stored in W register and the lower 8-bit of the address will be stored in Z register. Once the subroutine call is made, the processor pushes the current value of program counter on the stack. For example, here the subroutine is called call 2070. So program counter is pointing at this time to location 2043 and this location will be inserted into the stack and loads the program counter with 16-bit address of the subroutine which is stored in WZ register. So here the program counter content will be stored in stack and the new address of the subroutine will be loaded into program counter. So the content of WZ register will be loaded into program counter. Now the processor will start the execution of subroutine instructions. RET instruction. Once the subroutine has finished, the control will return to the main calling routine. In RET instruction, which is a 1-byte instruction, retrieve the return address which was stored into the stack. It will be retrieved from the stack and it will be loaded to the program counter to resume the execution where it left when the subroutine was called. The return instruction will initiate the retrieval of return address from the stack and load it into the program counter. These call and return instruction can be conditional. So first condition will be tested. If condition is found to be true, the call and return instruction will proceed. And the condition can be tested based on some flags value. These flags are carry flag, zero flag, sign flag and parity flag. Conditions are tested by checking the respective flag. If carry flag is being used, then the value of carry flag will be tested. In case of conditional call instruction, program is transferred to the subroutine if condition is true. Otherwise, main program is continued. In case of conditional return, The sequence returns to the main program if condition is met. Otherwise, sequence in subroutine is continued. So conditional calls based on the value of different flags. Conditional call instructions can be CC, call if carry, call the subroutine if carry flag is set, CNC, call if not carry, call the subroutine if carry is not set, CG, call subroutine if zero flag is set, CNG, call subroutine if zero flag is not set, CM, call subroutine if sign flag is set. Sign flag has 1 and 1 represent negative number, 0 represent positive number. So if CP, it calls subroutines if sign flag is not set. Conditional return RC returns from subroutines if carry flag is set. RNC returns from the subroutine if carry flag is not set. Return Z returns subroutines if zero flag is set. Return not Z returns subroutines if zero flag is not set. RM returns subroutine if sign flag is set. RP returns subroutine if sign flag is not set. RPE returns subroutines if parity flag is set. When parity flag is set, the parity is even. RPO returns subroutines if parity flag is not set. If parity flag has value 0 and 0 value denotes odd parity. The content of this lecture was taken from book Microprocessor, Architecture, Programming and Applications with 8085. Thank you. Happy learning.